learn about operational amplifiers. What is operational amplifier? If you remember, in the class, I explained how does dependent sources work, how do the dependent sources work. So like in dependent source, we know that they need an external power supply, and that external power supply can deliver power to the circuit. And if you remember when we discussed the voltage gain KV, I said that the KV is the output voltage over input voltage, and the same thing for KI, which is current source, which is output current over input current. We know that these voltage and current gain are definitely less than 1 for the circuits with independent sources. But if we have dependent sources, this gain can be more than 1, okay? Because the energy needed for amplifying the signal can be provided by the external power supplies connected to the active and independent sources. Okay, what now? Let's see what is the amplifier. Amplifier gets something and amplifies it, multiply it by an like coefficient. That coefficient could be any value from negative infinity to positive infinity. It doesn't mean that it should be definitely positive numbers or the numbers greater than 1 or less than 1. Any number from negative infinity up to positive infinity can be like the gain of our amplifiers. So this gain for both voltage and current, it's gain. This gain has a range of negative infinity to positive infinity, depending to the source. Okay, so first let's see how an OpAmp looks like. Here we have an OpAmp. Let me show you. Give me a minute. Okay. Here we have an operational amplifier. We show an operational amplifier with a triangle. So triangle is a symbol for operational amplifier, and it has inputs and outputs. Okay, let's see what inputs and outputs are connected to this operational amplifier. This is OpAmp. The operational amplifier has 2 inputs, 1 and 2. Each has a name. We show them with plus minus sign. For the plus input, we call it non-inverting input. So the plus one is non-inverting input. The negative input is called inverting input. Okay, we have 2 inputs. We have one output, which we call it just output. And of course, we have one external power supply connected to this circuit. The power supply has a voltage, negative and positive voltage. So the power supply connected to this OpAmp is shown like this. And on the top, we say positive power supply. And negative power supply. Okay. So positive power supply, let's say it's like a voltage, we call it plus VCC, plus VCC. It's a positive voltage. And negative power supply is negative VCC. Okay, how does this amplifier work? It gets two inputs, plus minus, subtract them, and multiply the result by a number. Okay, so what is that number? That number is like the gain of the amplifier. So amplifier has a gain equal to A. It gets the inputs, subtract them, multiply by A, and send it to the output. Okay, so definitely we can say, by the way, let me tell you something. Non-inverting input, we show it with V sub P, V positive, and inverting input, we show it with V sub N, negative voltage. Okay, so it's the way we show positive inverting and non-inverting input. Okay, so based on what I said, we know that output VO is the difference between VP minus VN multiplied by A. So it's the main equation of an amplifier. VO is equal to A times VP minus VN. Okay, so, but it's not like simple. We need to characterize it. Okay, we need to see which range, in which voltage range the amplifier is linear. If you remember, when we started our discussion on the resistor, I said that the resistor has a linear region and a non-linear region. In the linear region, the relationship between the voltage and current is linear, if you remember, linear, and up beyond those like a linear region, the voltage and current, they don't have any linear relationship. Okay, so that one was for resistor. What about what about the amplifier? The characteristic of amplifier is not a plot as a function of current and voltage, because the variables of a resistor is current and voltage. But here, the input of the amplifier is Vp minus Vn, and the output is Vo. So we need to characterize an amplifier based on these two variables. So let's just draw the characteristic curve. Okay, if we draw a characteristic curve, we need two axes, y-axis and x-axis. So x-axis is called Vp minus Vn, which is the difference between two input voltages. And Vo is the voltage we see in output. So first of all, because A is a constant number, which I will tell you what's the value. It's very large value, and for ideal OpAmp, it's infinity. But let's for now just focus on A as a number, because A is like a constant number. Vo is equal to A times Vp minus Vn. So the relationship is a linear relationship. Okay, so if we draw the line, I have a ruler here. Okay, if we draw a line, we see that the relationship between uh, voltage and current should be in this form. Okay, so but does this relationship is like it stands forever? So if we like increase the difference between Vp and Vn, how far this line can go? Can it go until the infinity or no? Definitely no. Somewhere we need to stop. Somewhere we need to stop. At which point? If you look, you see that the vertical axis is VO, and this voltage is provided by positive external power supply. So it's plus VCC. So we cannot go beyond plus VCC because the plus VCC is the maximum amount of the voltage that the external power can provide. So as soon as we reach to the value of VCC, let me show it to you. As soon as we reach to the value of plus VCC, this curve, this line has to be stopped. It cannot like move beyond the plus VCC because we don't have any like voltage more than that value. So after this point, the curve of the OpAmp characteristic will be a vertical line like this. Okay, so the same thing for the negative side. For the negative side, if we reach to negative VCC, if we reach to negative VCC minus VCC, we cannot like decrease the voltage in the output beyond this value because the voltage less than negative VCC is not available. So after that point, the relationship between input and output will be a vertical line. Okay, so this one is a characteristic of this one is the characteristic table, characteristic plot of an op-amp. Is it clear, or you have any question? Okay, now I have a question for you. Who can tell me what is what is the slope? What is the slope of this curve? What is the slope of this curve? The slope, definitely we know that is the like delta y over delta x. So I got exactly, I got one answer, so which is correct. The slope, which is like the delta y over delta x, is VO. It's not sorry, not VO. It's A. It's gain. Okay, it's gain. So gain is equal to a slope. So A is equal to a slope is equal to gain. Okay, so a slope is equal to gain. And what else do we have here? We have to give some names to these regions. Okay, so we have some regions here which we need to like kind of give them some names to make sure that we exactly know at which region we are. So if I separate these regions with these dashed lines from here for the positive x and here for the negative x, okay? So here we have two different regions. The region in the middle, which the relationship between output and input is linear, we call it linear mode. It means that the amplifier is operating linear. So we call it the linear mode. And the other two regions are saturation mode. Okay, we don't want to be in saturation mode. We always try to remain in the linear mode because if we are in the saturation mode, of course, there is no value. The output is constant, so nothing going to be amplified. Just the output is VCC or negative VCC. So what's the point of using an using an op amp? So we can directly connect those points to power supply and have VCC and negative VCC. We use OpAmp to get like the signal amplified. So we need to stay in the linear mode. So for which under which conditions we are in linear mode? We can say if A times Vp minus Vn, which is like the gain, is less than Vcc and greater than negative Vcc, okay, we are in linear mode. So then Vo is equal to A times Vp minus Vn. Okay, so if we are in linear mode, Vo is gain multiplied by the Vp minus Vn. Okay, what if we are in saturation mode? If A times Vp minus Vn is greater than plus Vcc, then Vo is equal to, it's not equal to A times Vp minus Vn, because A times Vp minus Vn is greater than Vcc, and we cannot move beyond Vcc. So we know that Vo is equal to plus Vcc. That's it. And for the negative side of saturation mode, we say if A times Vp minus Vn is less than negative Vcc, then Vo is equal to negative Vcc. Okay, so we got the point. We have an amplifier which works in two different regions. If it is in linear mode, the output is equal to gain times the voltage differences in the inputs. If we if we are in the saturation mode, the voltage in the output is either VCC or negative VCC. Any question? Okay. So this device is like placed in a chipset. Like if you go to the lab, there are some ICs and chips that are amplifier. Let me show you one example. For example, one of the ICs that we have for amplifier, it like in this shape, okay, and it has 8 pins. Pin 1, 2, 3, 4, 5, 6, 7, 8, okay, and inside it we have an amplifier. Vn is connected to pin number 2. Vn is connected to pin number 2. Vp is connected to pin number 3. Output is connected to pin number 6. Output is connected to pin number 6. We need two more signals, VCC and minus VCC. So plus VCC is connected to pin number 7, and negative VCC is connected to pin number 4, and pin number 8 is not connected, and pin number 1 is offset null. Offset null, which we set it on 0 for our measurement. So this one is like an example of an amplifier. Okay, any question? Okay. Now that we know what is an amplifier and how does it work, let's see what is inside an amplifier. What is inside an amplifier? Okay, so we so far we just saw a triangle, which I said that has inputs and outputs, and it amplifies the signal. But what is inside an amplifier? And we will see it here inside of and OpAmp. Okay, this one is like an OpAmp, and we have inputs and outputs. Here we have VP plus, here we have VN minus. These VP and VN in the like in the input are connected together to an a resistor. Here is the resistor called RI. So they are connected together, and we call it that resistor RI. So by the way, let's just show some currents. Of course, from a positive terminal, we have a current entering the uh, op amp called I sub P, and from a negative terminal, we have a current entering the terminal called IN. And what else do we have? Inside this op-amp, we have one dependent voltage source, which is connected to a resistor called RO and connected to the output, VO. And of course, we have a current going through the output called IO. What is the gain? What is the like the value of this dependent voltage source? Here is the point. The dependent voltage source has a value of A times Vp minus Vn. Okay, so the dependent voltage source uh, has a value of A times Vp minus Vn. Okay. For an ideal op amp, if we have an ideal op amp, we would like to have input resistance equal to infinity, output resistance equal to 0, and gain A equal to infinity. This one is for an ideal op amp, okay? But we don't have ideal op amp, and of course we don't like it, because if anything is infinity and 0, the output is always infinity. So, but in a real op amp, we have these values. A real op amp. In a real op amp, the input resistance Ri is a very large resistor, greater than 1 megahertz, less than 10 to the power of 12 ohm. The value of input resistor. The value of the output resistor is a small resistor, which is limited in a range of 10 and 100 ohms. And gain is very large value. It's 100,000 and 10 to the power of 8. So still we see that for the actual op amp, we have a very large gain. It is not infinity, but it's super high value. Okay, so we know that in order to be in to operate in linear mode. So let me just write it down. For OpAmp. Alex, you hear me?
Yes.
Oh, okay, good. For OpAmp to operate in the linear mode, the output voltage is bounded by which values? Can you tell me? Let's go up and take a look. So the output voltage in linear mode should be bounded by, do you remember? VCC and negative VCC. Okay, so the output should be between VCC and negative VCC in order to be operate in linear mode. Okay, so if it's the case, we can say that the VO should be less greater than negative VCC, less than VCC. What is VO? Of course, VO is A times Vp minus Vn, which should be less than plus VCC, greater than negative VCC. Let's divide the terms by A. So we will have Vp minus Vn, less than VCC over A, greater than negative VCC over A. Okay, something here is interesting. What is interesting? It usually VCC is 15 volt. VCC is 15 volt. And what about A? If you remember, the minimum value of A is 100K, and VCC is 15. So 15 over 100K, it's almost zero. Okay, so it tells that Vp minus Vn should be very small value in order to be remain in linear region. Theoretically, we can say that Vp should be equal to Vn, because in an ideal op-amp, we said that gain is infinity. So if gain is infinity, Vp minus Vn should be less than greater than zero. So Vp minus Vn should be equal to zero, and Vp should be equal to Vn. So in an ideal op-amp, Vp should be exactly equal to Vn in order to be remain and operate in linear region. In a real op-amp, Vp minus Vn should be very small values, let's say in the nanovolt, millivolt, in order to be operate in linear mode. Because if we go beyond these values and have Vp minus Vn, let's say, equal to 1 volt, of course, it's not in the linear region, because as I mentioned, VCC over A and negative VCC over A is almost a number almost equal to zero, very close to the zero. So we should keep Vp and Vn as close as possible to each other. So let me just write it down. Do you have any question? Okay, we can say the supply voltage. I have a question. Let me read the question. The question is, there a reason for the specific value for real op-amp as opposed to any other power of 10 for each? No, there is not a specific reason for. The question is that is there a reason for the specific values for real op amps as opposed to any other power of 10 for each? No, it's not like any specific reason. Just is a manufacturing process, and these the values that work like better than other values. No, there is no specific reason, but there is a specific reason to have the values for the output resistor very large, the value for input resistor very low, but not like exactly a specific number. Depending to the application we use, we might choose different op amps with different values. It depends to our application. Let's say if you study the transistors, they have a like amplifier parameter called beta. That beta has the different values from 10 to 10 hundred, sorry, from 10 to millions. Okay, so which one should we use depending to the application we want to use this transistor? The same thing here. Okay, so uh, the supply voltage VCC is usually 15 volts, while A is a very large number. Okay, so what's that large number? Usually 10 to the power of 5 or greater. Okay, so usually 10 to the power of 5 or greater. Okay, consequently, linear operation requires that Vp almost equal to Vn in order to be in linear mode. In ideal op amp, the voltage gain is assumed to be is assumed to be infinite. So A is infinite. In which case, linear operation requires Vp exactly equal to Vn. The input resistance R sub I of the ideal op amp is infinite. So the current entering both input terminals IP and IN. So R sub n, I said that in an ideal op-amp is equal to 0. I sub n. Sorry, R sub I here. Ri is equal to infinity. So if Ri is equal to infinity, can you tell me what is the value of IP and IN? The value of IP and IN should be equal to, any answer? Just think for a minute. Any answer? Okay, no answer? Because, okay, let me just help you. If IR is infinity, it means that open circuit. If it's open circuit, what is the current? Now give me the answer. IR, IP and IN is equal to 0. Okay? So, because I haven't received any answer, just I'm not sure if you guys hear me. One of you confirm that you hear me.
I hear you.
Oh, okay. So because the input resistance is equal to infinity, the both IP and IN are equal to 0. So in ideal op-amp, VP is equal to VN and IP is equal to IN is equal to 0. Okay, so we reach to this point. Okay, now that we are in this point, when I say VP is equal to VN and IO is equal to IN, for our circuits that we design by OpAmp, we assume that we have ideal OpAmps because the large values are very large and small values are very small. So we can like uh, assume that like the op-amp is ideal. Okay, so we can assume that the Ri here is infinity, Ro here is 0, and like the gain is infinity. Why? Because in the like in real op-amp also the values are very large, and we can just do this assumption. Okay, so let's just go ahead and do few simple op-amp problems. But the only thing that I want you remember, which are super important in order to solve any op-amp problem, you should consider few equations. The first equations, which is very important, is like that VP is always equal to VN. The second one, which is very important, is IP is equal to IN is equal to 0. Never ever forget these equations. And you relate, not equations, these are not equations, just a relationship. And of course, this one. Where is it? And of course, this one. Okay, so we should know this theory relationship. VO is always equal to A times VP minus VN, and the last but not the least relationships are here. VP is equal to VN and IP is equal to I, and don't forget these rules. Okay, so now that we know these rules, let's go ahead and do some examples. The first example by OpAmp, it's non-inverting amplifier. Non-inverting amplifier. What does non-inverting means? It means that if the Vp minus Vn. If not Vp minus Vn, sorry. If the input voltage is positive, the output voltage is also positive. If the input voltage is negative, the output voltage is also negative. Okay, so it's non-inverting. And here is the circuit. Here is the circuit. We have our OpAmp. And by the way, we don't need to show external power supplies every time we solve a problem for OpAmp because they always connected to external power supply and we don't have to show them. The VP is connected to input voltage called Vs. The output, which is here, it's VO. It's connected to the ground by two resistors called R1 and R2. And from the output side of the circuit, we take a feedback and connect it to the negative input. Okay? So we call this feedback loop. Feedback loop. Okay, this one is a non-inverting amplifier. So the output of this amplifier should be like a proportional of the input. Let's just analyze this circuit and see if we can find the output. Okay, the first thing first, do you remember the rules? Okay, the first thing regarding the positive terminal, what's the voltage of positive terminal? Vp is equal to what? Vp is equal to, just answer me, at least one of you. Vp is equal to?
Vn.
No, yeah, that's correct. But before that, look, the Vp is connected to what? Vp is directly connected to
The voltage source.
voltage source. Very good. So Vp is equal to Vs. Okay, it's the first step. And second step, what you said. You said Vp is equal to
Vn.
Vn. So Vp is equal to Vn is equal to Vs. So it's very important. We know that Vp is equal to Vs, Vp is equal to Vs equal to Vn. So it's very important. You should know this, okay? So don't forget. So Vp is equal to Vn equal to Vs. By the way, one thing we shouldn't forget, Ip is equal to 0 and In also is equal to 0. The current is equal to 0. There is no current. Okay. Now, let's look to the other side of the circuit. In the other side of the circuit, we have one node. Here, it's a node. You see the node? And I want to write a KCL node equation for this node. Okay. The first thing we should notice, what is the KCL? What does KCL say? The KCL says that the currents entering a node are equal to currents leaving the node. Is it right? Yes. So now I have a question. How many branches are connected to this node? You might say 1, 2, and 3. But we have something special. This branch here, okay? What's the current of this branch? Can you tell me?
0.
0. So this branch is not involved in writing the KCL because there is no current going through this branch. Okay, so we have two branches, 1 and 2. The third branch with like a feedback from output to the input includes no current. So we cannot just we don't need to include it in the equation. So let's write the KCL. So for the KCL, we say V naught over R2 plus V naught minus VO over R2 is equal to 0. Okay, any question for this one? Just I wrote the case here. But one other thing. Here, just let's see if you can answer this question. It's really like easy but useful answer. VP is equal to VN is equal to VS. Do you remember? And one more relationship that we need to notice here is here. V naught is equal to Vn because it's just connected with the wire. So V naught is equal to Vn. Okay, so we see that V naught and Vn are same. They're connected together by a wire. So as V naught is equal to Vn, we can write our equation in this form: Vn over R2 plus Vn minus Vo over R2 is equal to 0. Okay, now 1 over R1. Oh, sorry, the first one is, I think here, just I'm trying to show it. It shouldn't be R2, it's R1.
Mm-hmm.
R1 and R1, it's not R2. So 1 over R1 plus 1 over R2 times Vn is equal to 1 over R1 times Vo. As a result, Vo is equal to R1 plus R2 over R2 times Vs. And we see that at this moment, we have a relationship between input voltage and the output voltage. Okay, input voltage and output voltage. What is the gain of this circuit? Of course, I know that the gain of the amplifier itself is it's A. That's fine. Which we said it's infinity. But I'm not talking about the amplifier only. I'm talking about the circuit. What is the gain of entire circuit? The gain of entire circuit, of course, is equal to R1 plus R2 times, R1 plus R2 over R2, because VO over VS is equal to R1 plus R2 over R2. Okay, so we got to this point and we can call it KS, oh, no, sorry, KV, and it has a name. We call it closed loop gain. Closed loop gain. Okay. Now that we reach to this point, we see that the gain is defined. So now if we have the circuit and we want to have input 10 times, output 10 times greater than the input, the only thing we need to do is just kind of putting some resistors here in put R1 and R2 here is somehow that we need this equation equal to 10. For example, if we want to have KV equal to 10, so we can say, let's have R2 equal to 1K and R1 equal to 9K. If R2 is equal to 1K and K and R1 is equal to 9K, what is KV? KV is equal to 1K plus 9K over 1K is equal to 10. Okay, you see? So we got like the gain of 10. If we want to have a gain of 5, we can simply put like different values. We can say, we can put R2 1K, R1 4K over 1K is equal to 5. So it's like in our control, we can simply determine the gain of the circuit by changing the value of these two resistors. Any question? Okay, if you don't have any question, let me just draw the signal. If we have a signal like this, and it is like in our AC signal, which has a value of Vs and negative Vs, the output will be like this. They should be like, let me just, okay. And here is VO. And here is VO. And so this one is like amplifying the input. So when any input we apply, we get an amplified output. Any question? No question? Okay. So that's enough for today, and we will continue the lecture on amplifiers next week. Okay, let me just stop the recording.